In chemistry, sometimes the most important questions are the ones that are the absolute hardest to answer. Like, what if you needed to measure something that you literally couldn't isolate in a lab? Well, today, we're going to dive into one of chemistry's most elegant solutions to that exact problem. A truly brilliant shortcut for measuring the unmeasurable.
So, let's kick things off with a classic puzzle. On the screen, you see the reaction for making carbon monoxide from solid carbon and oxygen gas. Looks pretty simple, right? All you want to know is how much heat this thing gives off or absorbs. But, of course, there's a catch.
And the catch is a big one. You can't do it. I mean it. If you try to run this specific reaction in a laboratory, you will never get pure carbon monoxide. And that means you can't measure the heat for just this one reaction. So why not? What's going on?
Well, you've got two major roadblocks. First, if you try this at room temperature, it's so incredibly slow, you'd basically be waiting forever for anything to happen. So you think, okay, easy, let's crank up the heat. But the moment you do that, the reaction goes rogue. It doesn't just make the carbon monoxide you want, it starts making a bunch of carbon dioxide, CO2, at the same time. Now you have a mix, and you can't possibly tell how much heat came from which reaction. So, we're stuck.
Okay, so before we get to the clever workaround, let's talk about how chemists normally measure reaction heat, for reactions that actually behave themselves. They use a special piece of equipment. They use a thing called a calorimeter. And honestly, the concept is beautifully simple. You've got your reaction happening inside a sealed container, and that container is sitting in a liquid, usually water. As the reaction gives off heat, the water warms up, and you just measure that temperature change. Simple, direct, and usually very effective. So here's the more official definition. The key here is that the whole thing is really well insulated to trap all that heat. By measuring exactly how much the fluid's temperature changes, you can calculate the precise amount of energy the reaction released or absorbed. It's a fundamental tool in thermodynamics.
And this isn't just some toy in a university lab. These things get scaled up for industrial use and are absolutely critical for designing safe and efficient chemical plants. But here's the most important point. A calorimeter, no matter how big or fancy, is just a highly specialized thermometer. It is totally useless if the reaction itself is the problem. It can't magically separate the heat from our messy CO and CO2 mixture.
So, what do? We've hit a wall. Well, if you can't measure it directly, you figure out how to calculate it indirectly. And this is where we get to use a truly beautiful piece of logic, what I like to call chemistry's cleverest shortcut.
To really get this, just imagine you're climbing a mountain. You're standing at the base, and you want to get to the summit. Your total change in elevation, your final altitude minus your starting altitude, is going to be exactly the same whether you take a long, gentle, winding path to the top, or you decide to climb straight up a vertical cliff face. The path you took is completely irrelevant. All that matters is where you started and where you finished.
And this idea perfectly illustrates a core concept in science called a state function. It turns out the heat of a reaction, which chemists call enthalpy and give the symbol H, is a state function. Just like your elevation on that mountain, the total change in enthalpy for a reaction only depends on your starting chemicals and your final chemicals, not the specific pathway you took to get from one to the other.
This whole idea is formalized in what we call Hess's law. Now, I know this quote on the screen looks really dense and academic, but don't let that intimidate you. All it's really saying is what we just figured out with the mountain. If you can build your target reaction by adding, subtracting, or flipping other known reactions, you can just add, subtract, or flip their known heats to find the answer you're looking for. It's just algebra.
Okay, theory is one thing, but let's actually put this to work. It's time to go back to our carbon monoxide problem and use Hess's law to finally get the answer we couldn't measure. This diagram is our game plan. See that dashed line at the top? That's our target reaction. The direct path we can't measure, that's our vertical cliff face. But we can take a different route. We can take a measurable path down to an intermediate, carbon dioxide, and then take another measurable path from there to our final product. Since enthalpy is a state function, the total heat change of that detour has to be the same as the direct path.
So, what's our detour made of? Well, it's made of two reactions that are actually super easy to measure in a calorimeter. First, the complete combustion of carbon all the way to carbon dioxide, which releases about 393 kilojoules. And second, the combustion of carbon monoxide to carbon dioxide, which releases about 283. These are our building blocks. Okay, so here's how we put the puzzle together. Step 1. We take reaction 1 exactly as it is, because it's got carbon on the left right where we need it. Step 2, we need carbon monoxide on the right side of our final equation as a product, but in reaction 2, it's on the left. No problem. We just flip the entire reaction around. And if we reverse the reaction, we have to flip the sign of its heat, so it goes from negative to positive. Now for the magic. We add our two new equations together. See how there's a CO2 on the right in the first one and on the left in the second one? They cancel each other out. And what we're left with is our original target reaction.
And since we added the reactions, we just have to add their heats. Negative 393.51 plus a positive 282.99 gives us our final answer. The heat of formation for carbon monoxide is negative 110.52 kilojoules per mole. We just did it. We just measured the unmeasurable, and we never had to step foot in a lab. That is the power of this shortcut.
Now this is so much bigger than just a clever trick for one single problem. Hess's law is the foundation of a whole system that lets chemists calculate reaction heats from huge libraries of pre-measured data, letting them skip thousands of difficult, expensive, or even dangerous experiments. It's a really big deal.
One of the most important data sets out there is the standard heat of formation. This is simply the heat change from making 1 mole of any compound directly from its most basic elements. In fact, that number we just calculated for carbon monoxide, that was its standard heat of formation.
Another super useful data set is the standard heat of combustion. This is just the heat you get when you completely burn something in oxygen. And because burning things is generally pretty straightforward and easy to measure, scientists have built these massive, reliable tables of combustion data.
So let's see how this creates a whole system. Take a totally different reaction, the combustion of N-pentane, which is a component of gasoline. Do we need to build a special calorimeter and carefully burn this stuff to find its heat of reaction? Absolutely not. We can just build the answer from our data tables. Using Hess's law, you get this beautiful, simple formula. The total heat of any reaction is just the sum of the heats of formation of all the products minus the sum for all the reactants. Now you might wonder, why products minus reactants? Well, think back to the mountain. You're basically calculating the energy it takes to form the products from scratch, and then you're subtracting the energy it took to form the reactants from scratch. The difference between those two values is the net energy change for the reaction itself.
So for the combustion of N-pentane, we just look up the heats of formation for CO2, water, and pentane in a table, plug them into our simple formula, and boom, out comes the answer, negative 3509 kilojoules per mole. It's an unbelievably powerful and efficient way to map out the energy of almost any reaction you can think of.
So in the end, Hess's law is so much more than a calculation. It's a powerful demonstration of a deep principle. For some things, the path is completely irrelevant. It's all about the start and the finish. It really makes you wonder, right? What other seemingly impossible problems could we solve if we just focused on the destination instead of getting lost in the journey? Thanks for joining this explainer.